From the lab to your ears, you're listening to WonderLabs.
Hey everyone, and welcome to WonderLabs. If you enjoyed our last episode with Dr. Andrew Gallimore, fear not. This one is equally far out. In this episode, I speak with Professor Yasha Neiman. Yasha holds a PhD in physics from Tel Aviv University and is currently an assistant professor in the Quantum Gravity Unit at the Okinawa Institute of Science and Technology, OIST. Broadly, Yasha's work focuses on understanding the laws of nature, and he's particularly interested in understanding how gravity and quantum mechanics can coexist in a universe that's expanding at an accelerating rate. If that doesn't mean much to you right now, fear not. He explains all of that after a history lesson on quantum mechanics, general relativity, and the problems with the standard model of particle physics. Yasha weaves together a story that brings us into the present moment and what theoretical physicists spend their time thinking about. And, finally, why anyone else should care. Pay attention. Quantum gravity isn't easy, and every part of this episode is essential context. And by the end, you'll be glad you embarked on this wild journey to infinity. If you could use an extra particle physics primer, you can also head back to episode 2 and revisit our conversation with Joanna Huang from the Atlas experiment at CERN. Yasha is an eccentric character and a brilliant scientist. He's someone who sees science as a hedonistic pursuit, something that aligns well to fundamental physics, one of the few research areas where academics can actually sit and think in solitude. He brings energy and enthusiasm to challenging topics, and illustrates why fundamental physics has captured the imaginations of so many people. Our conversation captured mine, and I hope it captures yours. Professor Neiman.
Why, Chris, hello there.
Thank you very much for joining us today. Before we get into the most difficult problems in physics, I thought we could just start with something light and you could introduce yourself.
So, hello, and thanks for having me. My name is Yasha. I'm a theoretical physicist. I work here at OIST in Okinawa as an assistant professor in the quantum gravity group.
Wow, I do want to dive into quantum gravity and what that means, but for the sake of my own ignorance, I thought it might be nice if we could start off with a bit of context.
All right. So, I like to think about fundamental physics, which means essentially trying to meditate on the most fundamental laws of nature as we know them, and to dig deeper and uncover the more fundamental ones. And most of the time, this basically means taking things apart into smaller and smaller pieces and figuring out how the world works at smaller and smaller distance scales, and then understanding how the large, chunky, clunky world of our everyday eventually emerges from the smaller and smaller particles down there. And in that quest, the past few centuries have been a tremendous success, culminating in the 1970s in what we call the standard model of elementary particle physics, where we hit some seemingly bedrock level of what look to be elementary particles, with names like electrons and quarks and photons and neutrinos, and recently, finally, experimentally discovered the Higgs. So you get down to the fundamental particles and the forces between them. In fact, at that level, even the distinction between particles and forces gets somewhat blurred in a very nice way. So we have the electromagnetic force, the weak nuclear, the strong nuclear. The Higgs can count as a force as well, if you prefer. And the one force from our everyday life that is missing there is gravity. In fact, it's worth maybe mentioning that our everyday is completely dominated by gravity and electromagnetism. So that the other forces, the nuclear forces, we had to work hard to discover. Or everything we normally experience is our gravitational attraction to the Earth, and all else is electromagnetism in many and wonderful manifestations. And normally, we think of gravity as only a property of large things. So I experience the gravitational pull of the Earth revolves around the sun does its thing within the Milky Way galaxy, the galaxies do their cosmic dances, but already the gravitational force between the two of us sitting across a desk is too small for me to worry about, and you need to set up something like a basic university lab in order to measure such a thing. So we tend to see gravity only between very large bodies consisting of huge numbers of particles. Another way of saying this is that gravity is very weak. So the only reason we see it at all in everyday life is that, unlike all the other forces, it's cumulative. So the electric force, for example, sometimes attracts and sometimes repels, and this almost always, almost perfectly evens itself out. The gravitational force always attracts, so even though it is staggeringly weaker than everything else, it can eventually, when you get large enough, band together and start overwhelming the other forces. For example, me sitting here on a chair, not falling and not levitating, is a truce between the gravitational force of the entire Earth acting on my entire body versus some electric repulsion plus funny quantum effects between the bottommost atoms of me, let's not mention where exactly they lie, and the topmost atoms of the chair. So at the level of individual particles, without the opportunity to gang up in numbers, gravity is completely negligible and so traditionally not a part of particle physics. Now, we do have a wonderful theory, in a way, the most wonderful theory of all for describing the gravitational force, which we call general relativity. But it seems to stand apart from particle physics and never really needs to interfere, except if you continue digging into smaller and smaller distances. And this you will now have to do in your mind because we don't have the accelerators for it, but we know the rules and we know what should happen. So if you zoom in more and more and you try to localize particles to smaller and smaller chunks of space, then quantum mechanics and its uncertainty principle will force their energy to go higher and higher and higher.
What do you mean by that?
So the uncertainty principle tells us that you cannot at the same time know precisely the position and velocity of a particle. So if we zoom in more and more on the physics of smaller and smaller distances, one of the things we're doing is that we're forcing the particles to tell us their positions more and more precisely. And as a result, they have to become less and less precise, more and more all over the place in their velocities, running around faster and faster and more energetically, so that the physics of short distances is the same thing as high energies, which is why we need to burn all that electricity for the accelerator at CERN to bring protons up to ridiculously high energies in order to collide and probe smaller and smaller distances. But here we need to go much farther than that. And what will happen when particles become more and more energetic. So there is this little meme called E equals mc squared. It's like I don't remember the guy's name, some Jewish name, who came up with it. So in special relativity, particles that become more and more energetic also become heavier. And gravity responds to mass. So as you zoom in, gravity gradually becomes stronger. And it starts out very, very weak at the scales of our everyday, as we've been saying. So you need to zoom in very, very far in order for gravity between individual particles, not ganged up as planets and stars, to become noticeable against the normally much stronger electric and nuclear forces. And the length scale at which this is supposed to happen, which no one has ever observed, but we can calculate it, it's called the Planck scale, and is something like 10 to the minus 35 meters, which is 16 orders of magnitude smaller than anything we can probe with accelerators now. Then we are in the realm where you need to understand gravity at the quantum level, where both gravity matters and the peculiar behavior of individual particles. Now, why would you care about this? So, firstly, because such tiny, tiny, tiny distances at which things happen at very, very high energies, at very, very high densities, are actually supposed to occur in the universe all over the place. Because gravity, when it gets strong enough, if you just take a large enough star, it collapses stuff into black holes, where the density of matter seems to grow without limit, and you will eventually reach this realm, even though we cannot do that ourselves in our experiments. And for the universe itself, if you go far back enough in time, reverse the expansion of the Big Bang, you will get to earlier and earlier, hotter and hotter, denser and denser periods where, again, physics at these kinds of length scales will become important. So when we want money, we will say we need to understand black holes and we need to understand the Big Bang. But more honestly, for ourselves, it is a cool question. And the reason why it's a cool question is directly related to why it's a hard question. Because it forces us to reconcile two very different ways in which we learned to think the world.
So, in contrast to the money seeking activities of the cosmological scale, you instead now find yourself on a humble quest to understand the nature of reality by bringing gravity into the quantum fold.
Right. but now, let's go and tell ourselves what these words actually mean. So, what is this quantum fold? And what is this quantum mechanics? So, the essence of it is that in quantum mechanics, objects in the universe, dynamical things that can move and act and behave, do so in many different ways at once. They don't choose one place to be or one trajectory to follow or one value to have, but they try out everything at once. Now, what is this gravity of which you speak? So, gravity by now for us is code to a very specific view of the world, which Einstein called general relativity, which is that the shape, the geometry of space-time itself is also a thing that moves and wiggles and responds to other things that we're used to thinking of as matter. And both of these new ways of thinking are separately hard. It's hard to figure out how to calculate what even to calculate, how to properly think about a world, the shape of which is a dynamical creature following its own equations rather than given from above. It's hard to understand how to think about a world in which particles do several things at once.
So, how do you begin to think about that?
Well, you learn a lot of beautiful math, of course, because the real trick is to bring this stuff from the level of words. So the words are easy, but they tell you very little. So I remember how little I got of quantum mechanics from trying to read the popular books before actually learning it. But you need to actually learn it and actually see how the things work. But if you try to play both games at once, to think yourself a world in which all things that jiggle do many things at once, and in which space-time itself is one more thing that jiggles. So, how to think about many different histories, many different shapes of the universe itself coexisting and interacting with each other, that is a conceptual tall order that we've been struggling with for these many decades. So, the problem of quantum gravity is two things at once. It is how to figure out physics when distances get so small, energies get so large, that gravity between individual particles becomes important. And it is a very different sounding question of how to reconcile two different sets of deep and non-intuitive principles about the nature of reality.
So, how then are you going about that?
In recent decades, a surprising amount of progress on our humble problem has been made. And in my view, the progress that matters has been made under the rubric of string theory. Now, I can't really call myself a string theorist. I never studied it properly, and I don't directly use it. But I've come to think of myself as morally a string theorist, and I should soon tell you why. But 20 years ago or so, the string theorists have come up with an ingenious judo move to, you might say, solve, you might say, circumvent.
Hack, if we're using 21st century buzzwords.
Yes, hack the problem of quantum gravity. And the technical term for this is ADS-CFT. The more colloquial buzzword would be holography, where what they tell us is that instead of playing the game of digging deeper and deeper into smaller and smaller distances until you hit the realm where your space-time is quantum fluctuating and you don't know what to do. Instead of that, you can entirely reverse things. And this is yet one more way. So we started out saying gravity is physics of the very large, of stars and planets and galaxies. Then we corrected ourselves and saying, no, actually, gravity truly comes into its own, becomes important for individual particles in the realm of the very small. So no. Gravity is physics of the very small. It just so happens that we see it come together for huge chunks of matter. So what the string theorists decided to do is to throw it back into the realm of the very large, to reverse the drumbeat of the entire reductionist project of zooming in further and further, and instead to write the fundamental laws of the world at infinite distances.
Infinitely large distances.
Infinitely large distances from the vantage point not of a stronger and stronger microscope, which was what our colliders and so forth really are, not from a larger and larger microscope, but from a larger and larger, farther and farther away sphere at the boundary of the world, so to speak.
And by world, you mean universe.
Yeah. No, not not our little local Earth world, of course.
Hmm.
And there is a very subtle art in making this work, in actually managing to encode fundamental laws on the canvas of the very large instead of the very small. But once you manage to do that, you won against the puzzle of quantum gravity, because one way to say what happens is that you've zoomed out so far that you can no longer see the scale at which your space-time is quantum fluctuating. So you can forget about it. Another way is that once you've zoomed out far enough, then gravity itself ends up becoming negligible if you are very, very far away from any massive bodies that would generate it. And so you can forget about your general relativity, forget about your universe having geometry that is dynamical and alive, and live comfortably in the world as you knew it before general relativity came along to disturb you.
Before that unnamed Jewish guy.
Right. The one with the hair. And so, 20 years ago, the problem of quantum gravity was solved. And I've been, therefore, out of a job since age 15 or so.
And yet you're still here.
And yet I'm still here because it turns out it was solved, but not in the real world. Because also 20 years ago, at about the same time, a seemingly very unrelated development happened in observational astronomy. People have made the very surprising, at the time, discovery that we knew that the universe was expanding for many decades now. And everybody, cosmologists, the popular science books, the encyclopedias, Carl Sagan, they were all asking, will the gravitational pull of the matter slow down the expansion this way or that way? Will it slow it down enough to stop it completely? Or will it keep going but slower and slower? And then in the late 1990s, actual observations with telescopes, initially by counting distant supernovas, later by other ways as well, have shown us that no, the expansion of the universe is not slowing down at all, it's accelerating.
And that's a problem.
And that's a problem if you like easy answers. Because as soon as we know about the Big Bang, we understand that we can only see the universe up to some distance, up to some so-called cosmological horizon. Because the whole thing was born some finite amount of time ago, some 14 billion years, and light has only had so much time to travel from place to place, and light goes at a finite speed, so we can only see so far. But what people thought would happen is that we can wait longer and longer, allow the light more and more time to travel to us from farther and farther galaxies, and eventually see the universe in its entirety.
Seems almost too good to be true.
Almost too good to be true. Because once you learn that not only there is an expansion, but that the expansion is accelerating, it very quickly turns out that you will never see it all. That parts of the universe that are far enough away from you will run away so fast that their light will never reach you no matter how long you wait. And in fact, the prediction is that our cosmological horizon, instead of growing indefinitely, eventually gets stuck at some size, which is not very different from its current size now. So it will maybe grow by 20 more percent or so. But then, however much of the universe we're able to see, that's it. And you would think, so what? And for most of life's problems, that's all right. But if you were worrying about the fundamental problem of unifying gravity with quantum mechanics, and if your best trick in the book for solving it is to leave the small distances behind and run off instead to write your laws at the sphere at infinity, then suddenly you very sharply care when the sphere at infinity is taken away from you. So now suddenly there is a limit to how far we can zoom out. So the original problem where you zoom in too far and space begins to quantum fluctuate and you don't know what you are doing anymore, that essentially gives you a smallest length that you're allowed to think about. But now the universe with its accelerated expansion is giving you a largest length of which you are allowed to think. And both these things together are too much for us. So in the jargon, this whole business of the entire universe being visible or not, of having an accelerated expansion or not, is captured by a term called the cosmological constant. So the worlds which the string theorists have taught us to describe from the vantage point at infinity, they have a negative cosmological constant. And what the telescopes have shown us about the real world is that it has a positive one. So in my telling of the story, the original problem of reconciling quantum mechanics with general relativity is sort of, in a legalistic sense, solved at the small price of leaving the real world behind. And now there is a new problem, which is how to reconcile those two things with a third one, with our input from cosmology, that the universe is accelerating, that the cosmological constant is positive, that there is a largest distance that we would ever be able to see. So that is what I spend my life trying to think about.
Well, you certainly have your work cut out for you, and you have a great degree of confidence that your approach can work. Assuming you can get to a place where an elegant solution can be found, what then are the implications for physics, for humanity?
Well, no one said anything about being confident. In fact, us fundamental theorists have had to eat a lot of humble pie lately. The one thing that we can be confident about is that the universe somehow exists. That all the things we cannot figure out how they might fit together somehow do. And nature is smart enough and has an answer. Whether silly little we can come up with the answer and match nature's cleverness is a whole big question. Well, once upon a time, it would be absurd. People would not reasonably dare to dream to understand the laws of the universe, or even that the universe had laws. Then, during the last few centuries, we got ourselves spoiled. And with relative ease, which is, of course, discounting the life work of the smartest people in the world generation after generation, but with relative ease, we managed to dig deeper and deeper into the fabric of reality. But lately, it seems that we'll need to take a step back a little. And the enormous optimism from popular books from the 80s, the 90s, that theory of everything for physics is around the corner, that has been dissipated by some harsh encounters with reality, of which the discovery of the positive cosmological constant, of the accelerated expansion of the universe, has been just one. So we have now confined ourselves for a time. And this is where I think, to take the liberty of speaking for the string theorists, I'd say that I am morally a string theorist. We in this line of work have confined ourselves in a kind of tactical retreat. We hope that it's just temporary, but to playing with these imaginary worlds. So the imaginary world that's not expanding at an accelerated rate, that has its cosmological constant negative, that allows you to retreat to the sphere at infinity, the world we call anti-de Sitter space, we haven't thrown it away after discovering that it is not the real world, because for most of us, it is the best we have. And so an entire generation of theoretical physicists, including most of the postdocs in my group right now, they spend their time trying to understand that better and better, in the hope to become wiser in the process, to come back to the real world one day. So when I feel self-aggrandizing, I would say, well, I'm not one of them. Okay? I know the real world has a positive cosmological constant, that it has a finite cosmological horizon. But in fact, I'm not smart enough to do it in the real world either. So I end up selling my soul in some other place. And the model that I'm playing with is wildly unrealistic in some other ways. So we are being humble. We are chipping away at the space of ideas to try and see how things work out, even in principle, how they work out in toy examples that silly us, silly despite being significantly smarter than everybody a few decades ago, but silly, it seems, when faced with the next challenges that the real world is throwing at us. Sticking to our little toy systems, watering our little gardens of mathematical knowledge and conceptual understanding, hoping that we will one day become smart enough to understand the real world. Then, if you want to go the one step up in confidence and say, okay, we have succeeded, or our grandchildren have succeeded, and as Hawking and Brian Greene and friends promised us in the pop physics books, we have our theory of everything, or at least our theory of quantum gravity in the real world, then what have we as humanity gained? So there again, I think we need some humble pie, at least in the foreseeable horizons. So the most modern physics that has any practical application, that has found its way into technology, is probably around 1930. So general relativity itself has recently become applied in GPS. Quantum mechanics is now applied in things like transistors in our computers. Even things like antiparticles we use for medical imaging now every day. But that's about it. So none of the details of the weak and strong nuclear forces, nothing of what we've learned about the quarks inside the protons, nothing we've learned about the Higgs. None of this has found its way into applied technology. So it would be terribly presumptuous to start dreaming about how the deeper stuff might ever play out in the real world. But the way I'm thinking about it is usually from a different angle altogether, which is that humanity needs projects. We need things to marvel at and to be proud of. And that's the real reason for doing, let's say, space exploration. And even better, manned space exploration. Even though from almost every other point of view, it's a complete waste of money. You don't need to travel to the planets and stars at all. And if you really must, then it's cheaper with robots, except that we want the sense of adventure. And that is no small thing. So the reason I can honestly give from the wider perspective of normal people who haven't spent many years meditating on this stuff is that when I was little and reading the popular books about the stuff achieved back in the early 20th century, in the 60s and the 70s, the speculations that people have come up with since, was that got me terribly excited and optimistic about what people can do. And it feels to me like on both fronts, both in space exploration and in fundamental physics, we started lagging and failing to capture the public imagination the way we used to. And that is why we all must get our act together and work harder at our esoteric little problems, because people want their imagination fed, and they are smart enough to realize that feeding it with real hard-earned discovered truths about the underlying nature of the world is better than most everything else.
And if that's not a wonderful place to wrap that part up, I don't know what is. So, standing on the shoulders of giants, eating plenty of humble pie, and ignoring any tangible applications and focusing on the most important one, which is capturing our imagination. Professor Neiman, thank you very much for that whirlwind tour.
Thanks a bunch.
One thing we do like to do to wrap things up is a quick fire round. How do you feel about that?
Okay, let's go.
Could you explain in one or two sentences what it is that you do?
I try to understand how to describe a universe in which there is both a smallest and a largest thinkable length scale.
Beyond your own areas of interest, which emerging field in science or tech are you most excited about?
I'd say I'm terrified of most of the exciting ones.
You and I both.
So the obvious picks would be now biotech and artificial intelligence, and we can only hope that we'll be able to navigate that.
What is a common misconception about your area of research? Something that if you could wave a magic wand and have everybody instantly understand it, what would that be?
The humble pie. That we are not our elders from 30 years ago who promised instant success. We should not be judged on their hubris and failure.
Is there a particular tool, piece of equipment, or software that you particularly enjoy using beyond your own brain?
All I can do is give the much-deserved shout-out to the Linux operating system.
Shout out to the penguin.
Hear, hear.
Do you have a favorite science-related joke or fact you could share with us?
My favorite fact would easily be, if I can lump some things together, that the yellow color of gold, the runniness of mercury, the viscosity of mayonnaise and wall paint are all now understood in terms of quantum relativistic physics. They all require knowing both quantum mechanics and special relativity.
And I believe there's actually a separate talk on the color of gold.
Yes, go listen to the TEDx. Don't watch I Look Terrible, but listen.
What is it with us and gold? Is there maybe some rule book to human civilization where it says in a very serious tone of voice, there is this metal called gold, it's element number 79 in the periodic table, and that is what you're going to use for your currency and wear as jewelry, and that's what you're going to put in your vaults and in your treasure chests and go to war for. Very important element number 79, don't forget.
Professor Neiman, where can people go to find out more about your work?
In this instance, I will be a megalomaniac and refer you to the website of our group at OIST and to my own recorded talks there. That is groups.oist for Okinawa Institute of Science and Technology .jp, we're in Japan, you see, /QGU for Quantum Gravity Unit.
Professor Yasha Neiman, thank you so much.
Thank you.
Thanks for tuning into WonderLabs. If you enjoyed this episode, please take a moment to subscribe, leave a review, and share it with others who you think might enjoy it. You can also email us at wonderlabspod@gmail.com. I'm your host, Chris Richardson. Our branding was designed by Lloyd Preston Allen, and our jingle was produced by T. Fitzgerald at For The Record. That's soundcloud.com/WEAREFTR. Special thanks go out to Liliana Laborde-Dozian. We'll see you next time.